Good morning, good afternoon, good evening, class. This is Mr. Erosena, and today we're going to talk about the electrochemical cell. We've already done a lab on this, where we actually created an electrochemical cell, and we're able to measure the voltage that was created from it. Now, I'm not entirely sure why, but the voltages we measured in the lab were actually quite a bit smaller than what they should have been. And I'm still not entirely sure why that was the case. It could have been the concentrations we were using weren't correct, or just maybe the electrodes weren't properly scrubbed down or whatever, but not entirely sure. At the very least, though, at least you guys were able to create some voltage, even though most of the voltages end up being very, very low. Anyways, today we're going to discuss a little bit more about the what actually goes on during the electrochemical cell process. All right. So first things first. An electrochemical cell is composed of basically two halves. You have one metal and you have another metal. Now each metal is what's called an electrode. An electrode is basically just a conductor, so any conducting material, and a half reaction occurs at that conductor. Now there are two types of two types of electrodes. There is the anode and the cathode. Now the anode, this is where oxidation occurs. So the anode is the metal that gives up electrons. It creates electrons. The metal at the anode gets oxidized, and then you have this excess amount of electrons sitting at the anode. Okay. I know in the lab handout I gave you guys the other day, it said that the anode is the one that gets the electrons. It's kind of misleading. The anode is the one where the electrons are generated. Okay. Now the anode, because it has a lot of extra electrons, this is where oddly enough, the anions travel towards the anode. Okay. Now the next electrode is the cathode. The cathode is kind of the opposite of the anode. So the cathode is where the reduction occurs. And the cathode, because of reduction, the cathode ends up absorbing the electrons, okay, from whatever substance is being reduced. Okay. And then the cathode is where the cations travel towards. Okay, those are the two electrodes. You have an anode that creates electrons because it's being oxidized, and you have a cathode which absorbs electrons because it is being reduced. Okay, and every electrochemical cell is basically built on this principle where you have one anode that undergoes oxidation, and you have one cathode that undergoes reduction. Okay. Now, if you can't quite remember that, we have another mnemonic that helps us remember this, and it's called, the mnemonic is an ox cared. Okay, ox cared. And basically, this says that anode oxidizes. Okay, so the anode electrode oxidizes, and the cathode electrode reduces. Okay, so oxidizes is loss of electrons, or sneaky trick, gain of oxygen, and the reduction is a gain of electrons, gains electrons. So the cathode gains electrons, or it loses oxygen. Okay. So that's the definitions of what happens at the anode and the cathode. So the anode, the actual electrode, gets oxidized, so it becomes, I guess, less metallic, while the cathode gains electrons, so it becomes reduced and becomes more metallic. Okay. If you're using metal electrodes. As an example, here is a zinc-copper electrochemical cell. We have zinc, but we didn't have the right solutions for it. So what's the anode? What's the cathode? Well, the first step is to basically identify what are the half reactions? So this is what we did in our lab. So in the zinc half, we have two possible reactions. We can get the zinc 2 plus gaining electrons to form solid zinc, or you can have the zinc turning into zinc 2 plus and giving up 2 electrons. In the copper side, you have the same thing. You have the copper 2 plus gaining 2 electrons going to copper, or the copper giving up 2 electrons to become copper ions. So which one is it? Which one? Which one? And as I mentioned in our lab, we just have to decide, okay, we pick the one that's more likely to oxidize, so the stronger reducing agent, and the one that's more likely to reduce, or the stronger oxidizing agent. We pick those two, and that'll be our reactions. So in this case of the copper, I do believe this is the strongest oxidizing agent, and this is the strongest reducing agent. So this reaction would be the oxidizing reaction, and this reaction would be the reduction reaction. So there's my reduction, there's my oxidation. There you go. And that is how we would determine what actually happens. At the cathode, the equilibrium is disturbed because you have a lot of extra electrons moving towards the cathode. Okay, this forces the cathode to reduce because you have a bunch of extra electrons going there. So we've determined that this is the reduction reaction, so that's going to happen at the cathode. And because of all the extra electrons, the copper gains the copper ions that are in solution can absorb the electrons, and then they can become solid copper, which ends up getting placed on top of the copper electrode. Now overall, the electrons flow from the anode to the cathode at this point. Okay. All right. Now the salt bridge, as we saw, that serves somewhat of some purpose. The salt bridge allows water and certain ions to pass through it. And if you guys have observed your reaction the following day, you'll notice that some of the coloration bled into the little U-tube, and that's because the ions the ions are slowly making their way through that U-tube to the other side. Okay. Now, the salt bridge does prevent complete free mixing of the solution, so the electrons would prefer to travel through the circuit as opposed to traveling through the salt bridge, because traveling through the circuit is a lot easier. It's a lot easier. Okay. So basically, if I were to show this diagram again, what happens is that, so this zinc starts dumping a lot of zinc ions into here. Zinc ions, zinc ions, zinc ions. And here you've got a bunch of copper 2 plus ions. Copper 2 plus ions. Copper 2 plus ions. So as the zinc gets turned into ions, all these extra electrons start building up here on the anode. And when you connect the wire, the electrons travel through the wire to here in the copper, and then that allows the copper ions to absorb these extra electrons and then start becoming actual solid copper. Okay. Now in the salt bridge, in order to continue this, the salt bridge, the ions, these positive zinc ions are going to be attracted to this electrode, because this electrode is gaining electrons, because the electrons again are leaving the anode, going through the circuit and traveling to the cathode. So these zinc ions will slowly move up into the salt bridge and go this way. Okay. And if left long enough, they'll eventually all end up over here. Okay. Now the negative ions that are present in the copper solution here, the negative ions here, because again the copper ions had to come from some ionic compound, so usually like a copper nitrate or copper sulfate, they would end up traveling through the salt bridge this way. So any negative ions that are present in this would end up going up the salt bridge and out this way. Okay. There we go. And part of the reason for that is, again, because the electrons are leaving the anode, so the anode is actually becoming slightly more positive. The electrons are heading towards the cathode, so the cathode is becoming slightly more negative, and that's going to push away these negative ions towards the salt, or through the salt bridge out this way. Okay. All right. So as a recap, at the anode, the zinc ions, or the positive ions at the anode, will move away from the anode. Some of them will move towards the salt bridge because they're being attracted to the cathode. The negative ions move towards the anode from the cathode. The cathode will be some negative ions there, so they start moving towards the anode. Okay. At the cathode, the opposite kind of occurs because the cathode is gaining a bunch of electrons. It's going to attract the immediate positive ions, which in our cell case ends up being the positive copper ions. And then it starts to repel the negative ions that are present, pushing them towards the salt tube, towards the other half cell. Okay. Yes, and this is how all batteries pretty much work this way. Okay. Eventually, the movement of ions stops because the electrodes have either gained all the copper ions that are in the solution, or the zinc electrode has completely disintegrated. Okay. And you guys will probably notice this if you haven't already looked at the cells you've set up. You should notice that whichever whichever metal you decided was being oxidized, or was the oxidizing reaction, that one should look a lot more rusted or a lot more corroded than when you first started the experiment. All right, with that, your assignment is as follows. We skipped a section, but that's okay. I'll go over that again when I get back to class because it's a little bit more involving than balancing full redox reactions. Because you have to balance the full redox reaction and then you have to do titration math. So we're kind of combining two different processes, and it will be a little bit more involving. But we'll discuss that after when I get back. Okay, there's your assignment today. 2 questions. If you like this, like, comment, subscribe, and I will see you guys later.